Chapter 4, Structure of Atom, Class 9th, CBSE based. Atoms were initially thought to be indivisible entities by John Dalton. However, by the end of the 19th century, scientists discovered subatomic particles such as electrons, protons, and neutrons. These discoveries led to the development of modern atomic models. Below is a step-by-step explanation of the structure of atoms, their subatomic particles, and the evolution of atomic models. 1. Subatomic particles. Atoms are made up of three main subatomic particles: electrons, protons, and neutrons. A. Electrons. Discovery of electrons. J. Thomson discovered the electron in 1897 while conducting an experiment with cathode rays. Experiment, cathode ray experiment. Thomson used a cathode ray tube, a glass tube with very little air, and applied high voltage across two metal plates called electrodes. When the electricity passed through, a stream of particles, which he called cathode rays, moved from the negative electrode, cathode, to the positive electrode, anode. He noticed that these rays were made of very tiny, negatively charged particles. These particles were much smaller than atoms and were eventually called electrons. Characteristics of electrons. Charge of electron. Electrons have a negative charge. The specific charge of an electron is minus 1.6 times power of 10 minus 19 coulombs, C. This negative charge was later confirmed by Robert Millikan in his famous oil drop experiment. The negative charge on electrons balances the positive charge on protons in an atom, making the overall charge of the atom neutral. Mass of electron. The mass of an electron is very small, 9.1 times power of 10 minus 31 kilograms. This means electrons are almost 2000 times lighter than protons or neutrons. Electrons don't contribute much to the mass of an atom, but they are very important for its behavior. Importance of electrons. Electrons are found outside the nucleus of an atom, in areas called shells or energy levels. They are responsible for the chemical properties of an element, how it reacts with other elements. The formation of chemical bonds between atoms to form compounds. The number of electrons in an atom is equal to the number of protons, ensuring that the atom is neutral overall. B. Protons. Discovery of protons. The discovery of the proton can be credited to E. Goldstein. He conducted an experiment that led to the identification of these important particles inside atoms. Experiment, anode ray, canal ray, experiment. Goldstein used a special type of tube called a discharge tube, similar to a glass tube with little air inside. He applied high voltage between two electrodes, positive, anode, and negative, cathode. When he did this, a glowing stream of rays moved in the opposite direction of the cathode rays, which were negative particles. These rays were later called anode rays or canal rays. By studying these rays, Goldstein discovered that they were made of positively charged particles. These particles are what we now call protons. Characteristics of protons. Charge of proton. Protons have a positive charge. The amount of this positive charge is very specific. The charge of a proton is 1.6 times power of 10⁻⁹ coulombs, c. This means protons are positively charged particles in the atom. Mass of proton. The mass of a proton is about 1.673 times power of 10⁻24 grams. This is about 1,840 times heavier than the mass of an electron. While electrons are extremely light, protons are much heavier and contribute to the majority of an atom's mass. Importance of protons. Protons are found inside the nucleus of an atom, at the center. Along with neutrons, protons make up the mass of the atom. The number of protons in an atom determines what type of element it is. For example, hydrogen has 1 proton. Helium has 2 protons, and so on. The number of protons in an atom is called the atomic number of the element, and it defines the element's identity. See neutrons. Discovery of neutrons. In 1932, James Chadwick made a significant discovery in atomic structure by identifying the neutron. To understand how this happened, let's break it down step by step. Experiment details. Chadwick was experimenting with elements like lithium, a light element. He bombarded these elements with alpha particles. Alpha particles are positively charged particles that come from radioactive materials. When these alpha particles hit the lithium atoms, they knocked out some new particles from the lithium. These new particles had no charge, meaning they were not attracted to either positive or negative forces. Chadwick named these new particles neutrons because they were neutral, neither positively nor negatively charged. Characteristics of neutrons. No charge. Neutrons have zero charge, which makes them different from protons, positive charge, and electrons, negative charge. They do not get attracted or repelled by other charged particles. Mass of neutron. Neutrons have almost the same mass as protons. The mass of a neutron is very slightly larger than that of a proton, but close enough that we can say they are nearly equal. Important point: neutrons and hydrogen. While most atoms have neutrons in their nucleus, protium, superscript 1H, which is a type of hydrogen atom, does not have any neutrons. It only contains 1 proton and 1 electron. This is an important exception to the general structure of atoms. 2 atomic models. Various scientists proposed different models of the atom to explain the structure and arrangement of subatomic particles. A. Thomson's model of atom. Thomson proposed that atoms are composed of a positively charged sphere with negatively charged electrons embedded in it, similar to the seeds in a watermelon. Limitation: this model could not explain the results of other atomic experiments and was eventually discarded. B. Rutherford's model of atom. Alpha-ray scattering experiment. Rutherford bombarded a thin gold foil with alpha particles, helium nuclei. Observations: most alpha particles passed through the foil undeflected. Some particles were deflected at small angles. A few bounced back, indicating a dense center in the atom. Conclusions: atoms are mostly empty space. A small, dense, positively charged nucleus is at the center. Electrons revolve around the nucleus in well-defined orbits. Drawback: according to classical physics, revolving electrons should lose energy and eventually spiral into the nucleus, making atoms unstable, which is not observed in nature. See Bohr's model of atom. To address Rutherford's model's instability, Niels Bohr proposed that electrons revolve in fixed orbits, called discrete orbits. Electrons do not radiate energy while in these fixed orbits. Energy is emitted or absorbed only when electrons jump from one orbit to another. 3. Atomic number and mass number. A. Atomic number, Z. Definition: the number of protons in the nucleus of an atom. The atomic number uniquely identifies an element. For neutral atoms, the number of electrons equals the number of protons. B. Mass number, A. Definition: the sum of protons and neutrons in an atom's nucleus. Formula: mass number, A, is equal to number of protons plus number of neutrons. For electron distribution in an atom, Bohr scheme. The arrangement of electrons in various shells around the nucleus follows the Bohr scheme. Rule: each shell can hold a maximum number of electrons as determined by the formula 2n superscript 2, where n is the shell number. K shell, n is equal to 1 maximum 2 electrons. L shell, n is equal to 2 maximum 8 electrons. M shell, n is equal to 3 maximum 18 electrons. N shell, n is equal to 4 maximum 32 electrons. Example: for calcium, atomic number is equal to 20, the electron configuration is K is equal to 2 electrons. L is equal to 8 electrons. M is equal to 8 electrons. N is equal to 2 electrons. 5 valence shell and valence electrons. Valence shell, the outermost shell of an atom. Valence electrons, electrons present in the outermost shell. Example, sodium, Na, atomic number is equal to 11, has a configuration of 2, 8, 1. It has one valence electron. Valency, the number of electrons an atom gains, loses, or shares to achieve a stable configuration, usually 8 electrons in the valence shell. Valency of a metal is equal to no of valence electrons in its atom. Valency of a nonmetal is equal to 8 no of valence electrons in its atom. Note, the valency of hydrogen is equal to number of valence electrons, which is 1. 6 isotopes and isobars. Isotopes. Atoms of the same element with the same atomic number but different mass numbers. Example, chlorine has 2 isotopes. Chlorine, atomic number is equal to 17 and mass number is equal to 35, and chlorine, atomic number is equal to 17 and mass number is equal to 37. Uses of isotopes. Uranium isotopes are used as fuel in nuclear reactors. Cobalt isotopes are used in cancer treatment. Iodine isotopes help in treating goiter. Isobars. Atoms of different elements with the same mass number but different atomic numbers. Example, argon, atomic number is equal to 18 and mass number is equal to 40, and calcium, atomic number is equal to 20 and mass number is equal to 40.